Hello, everyone. Thanks for joining my presentation about experimentation at GetYourGuide. Before I start with the talk, I would like to share a short video of a cooking class that I have attended 2 weeks ago in Crete. You can see here the moment when I understood why I gained 3 kilograms in just 2 weeks of vacation. But honestly, it was totally worth it because the food tasted amazing. And now you might be wondering why I'm telling you that. So we have this tradition at GetYourGuide that we start every presentation with a look back to our last vacation. And that's because GetYourGuide is a travel company unlocking unforgettable experiences like these to millions of customers around the world. And to continuously improve our product, we rely on experimentation. Let me quickly clarify why experimentation is so important for every product organization. Here's a schematic representation of a product development cycle. We usually try to optimize our product for our customer needs, and to do so, we come up with hypotheses about their needs. Then we implement a solution, and then we run an experiment to validate our initial hypothesis. Finally, we either find out that this is successful, and we roll out to all our customers, or we learn and iterate. And then we do the same thing again and again and again and again. And generally, the faster you spin through this process, the faster you'll make your customers happy. And therefore, you should always address the bottleneck in this process. And for many companies, like GetYourGuide, this was experimentation. And for that reason, I would like to share our learnings with you today. Let me first clarify what we mean by democratizing experimentation. At GetYourGuide, it was all about enabling product teams to run experiments independently. And to achieve that, we had to focus on various aspects, and I want to discuss the following 3 with you today. First, standardization. We had to ensure that everyone is using the same tools to validate their hypothesis. And that, for example, includes metric definitions, data sources, but also statistical implementations. Next, we have efficiency. To make our product optimization wheel spin as fast as possible, we had to ensure that we validate our hypothesis in the shortest amount of time. And finally, reliability. The best-looking test results are worth nothing if they are not trustworthy, right? There are also other important pillars, but I want to focus on the more technical ones today. So let's start with standardization. Our biggest pain points to standardize our experimentation platform at GetYourGuide were metric definitions and statistical calculations. When we started the projects, metrics and also statistics were defined in Databricks notebooks, huge SQL queries, or even in Looker. And you cannot imagine how many times we have seen similar but slightly different implementations to calculate the confidence interval. For metrics, it was important for us to have all definitions in one place and well documented. Furthermore, it was important that anyone can contribute new metrics and that they are reusable across teams. And for statistical calculations, we wanted to ensure that all experiment results are based on the same methodology so that they are comparable. It was important for us to establish a clear structure to how metrics are being defined. To enable flexibility and modularity, every metric is delivered in 3 consecutive layers. First, you have a numerical value or just a flag in the unit level aggregation, where unit level refers to the unit of randomization of your experiment. We usually refer to this as visitors, or other platforms. platforms or companies use users or customers or whatever. Second, there is a set of aggregated values on the experiment variation or experiment group level. And finally, we have a statistical layer where we define metric objects, including, for example, numerator and denominator for ratio metrics, and also standard deviations and so on. In this example here, you can see how we define the metric in the unit level layer. In this case, we are calculating the number of bookings for each experiment unit. And at the top of the file, you can see a bit of documentation containing the purpose of the metric and the owner. The query only needs to return two columns here, unit ID and metric value. In the later data table examples, you will also see columns like experiment ID, metric name, but such information gets added automatically. Now you can see a bit of Ginger syntax here in the metric source. And this is really important for us to handle data dependencies, which I will touch on later. And you can also see placeholders in the filters. They get replaced during runtime by our query resolver with the individual experiment configuration values. Now here you can see an example of how we store the data in each layer. So again, in all layers, we are specifying the experiment ID, the metric name, the metric value, and the variation, of course. And in the unit level layer, you have a unit level resolution, so you can see the unit ID there. Then in the variation level layer, we are aggregating this on a variation level. And then finally, in the statistical layer, here in this example, we are creating a ratio metric using the number of bookings and the number of visitors from the variation layer to create a KPI, bookings per visitor. So a few key takeaways here are try to establish a clear structure for metric definitions, as for example, how we did on a unit and variation level. Document every metric. You want to make them reusable across teams and have clear ownership to keep them up to date. Another important aspect, as already mentioned, was the standardization of recurring statistical implementations. So when we started the project, important statistical implementations, like for example, the calculation of p-values, confidence intervals, and significance was implemented in Looker. And the problem with that was that it is really limited, the capabilities of Looker, and we couldn't implement more advanced methods like, for example, sequential testing. For that reason, we implemented a dedicated toolkit for statistical implementations to centralize all those implementations. And we are using this in our production framework. But most importantly, we boosted the adaptation of this toolkit and the calculations by pre-installing this onto our interactive Databricks clusters so that analysts and data scientists can simply import this when they need to. In this small API example, you can see how an analyst, for example, would use the toolkit in a Databricks notebook. As it is pre-installed on all our interactive clusters, they can simply import the required classes. They can then define a control and treatment metric, instantiate the analysis by defining the error bounds, and finally run a significance test. A few key takeaways here are try to centralize all the statistical calculations in one dedicated repository and ensure that it is easily accessible. Also implement an API that's not only good for production use, but also for ad-hoc use cases. Coming to efficiency, with regards to efficiency, we mostly struggled with long experiment runtimes and the level of self-service. The experiment runtime is an important aspect for every experimenter. And of course, we want to evaluate our hypothesis in the shortest amount of time, but at the same time maintain statistical rigor. But as the experimentation team, another important aspect is also the level of self-service, because ideally everyone should be autonomously handling the life cycle of an experiment. Otherwise, our experimentation team would need a significant headcount, but at GetYourGuide, we are just 3 FTE working on the platform. Optimizing experiment runtimes without losing statistical rigor is difficult, but we have found a few features that are beneficial. First of all, we are using variance reduction methods like Cupid, which uses pre-experiment data to create an adjusted experiment outcome by removing predictable variation. This leads to less variance, smaller confidence intervals, and eventually shorter runtimes. We can see that this implementation leads to at least 10% runtime reduction on all our experiments. Second, we are using sequential testing, which solves an issue often referred to as the peaking problem in experimentation. For example, if you are using a t-test on your experiment evaluation and stop the test based on intermediate test results, then you are most likely inflating your false positive error rate. And to overcome this problem and to let experimenters stop tests early, we have implemented sequential testing. We have discussed this a lot in our blog posts and previous conferences. I linked our blog posts here, and also our implementation of sequential testing is open source, so feel free to give it a look. The last feature we are offering to shorten experiment runtimes is using upper funnel proxy metrics. Because these proxy metrics usually have higher baseline values, you can detect the same relative change in a shorter amount of time. However, they alter your original error bounds and are only useful when there's a really strong relationship between the proxy metric and your original variable that you want to optimize. So here you always need to have a case-by-case consideration if this is a valid approach. Now, we are continuously adding more features to our platform, as for example, the ones that I just described, and this adds user-facing complexity to our platform. And to maintain and elevate the level of self-service in our platform, we are implementing various features that help experimenters to independently manage their experiments. And I want to discuss the most impactful ones with you. First of all, we have implemented a preset feature so that lets experimenters configure repeating experiment configurations and let them reuse them. This is really helpful because it reduces the number of support requests and also reduces the number of experiment restarts. Experimenters often struggle with an appropriate runtime of their experiments. It's difficult for them to calculate how long they have to run the tests and to conduct a proper power analysis. We have automated the simple sample size calculation and added a runtime estimate, so that helps experimenters to properly power their tests and also helps them to decide when they need to stop the test. Also, sometimes experimenters are overwhelmed by the breadth of results that we are exposing on our reports, and for that reason we have implemented a decision engine and prominently exposed the results to the experimenters. In this decision engine, it doesn't only take into consideration the success metric and the support metrics, but also health checks like, for example, sample ratio mismatch test and the described power calculations. By the way, on the slide you can see some output examples of this decision engine. Finally, we have implemented an API for analysts to re-trigger experiment analyses. This is helpful whenever certain metrics and dimensions have not been calculated for past experiments, and this could happen, for example, when metrics were simply not implemented back when the experiment was started, or because they have been forgotten on the experiment configurations. For such cases, analysts can call a function that we have called trigger experiment calculation by defining the experiment ID, metric, a list of metrics, and a list of dimensions right from their Databricks notebook. And this will trigger a Airflow deck running through all the pre-aggregations necessary and all the statistical calculations. Then the results will be stored in our Databricks warehouse and can be consumed by the analysts in their notebook again. With this setup, we are enabling analysts to easily create experiment deep dives analysis in a standardized process. Main takeaways are try to simplify the experiment lifecycle management as much as possible. Implement features to reuse experiment configurations, automate runtime and power calculations, implement guided decision making, and integrated ad hoc analysis capabilities. Finally, let's talk about reliability. Our biggest reliability pain points were problematic contributions to our platform and managing data dependencies. On the one hand, we want to allow users to add new metric definitions and analysts to add new capabilities to our statistical toolkit, but at the same time, we have to safeguard our platform against bad contributions that might, for example, break our pipelines or introduce errors into our statistics. Also, every new metric definition could create new data dependencies, so we had to find a scalable way to manage those. Generally, we are safeguarding our platform through end-to-end testing. These tests are executed in every contribution in our CI/CD pipeline, and for metric definitions, new or adjusted queries get executed with standardized experiment parameters. This helps us to understand if the syntax is correct, ensures that we have sufficient data access privileges, and also monitors the runtime and the results count. With those checks in place, we can catch most of the contributions that would cause major harm to our pipelines. For the end-to-end tests on statistical calculations, we have a three-step process. So first of all, we are recalculating yesterday's experiment results based on the development branch, and then we compare the data set with our production data sets. Now, if there are any unexpected changes, then we just reject the deployment. And this setup is far from perfect, and we are continuously improving it, but it already catches most of the harmful contributions and ensures trustworthiness of our platform. With regards to managing data dependencies, you have already seen a key element of it in our unit-level metric definition. So in all metric definitions, data sources are defined with standardized Ginger syntax. This helps our CI/CD process to systematically recognize these dependencies and stores them into Airflow variables that maintains all those dependencies. This Airflow variable is then used to dynamically create the sensors of our experimentation deck every day. And in this deck, all the experiments get calculated independently, depending on when their dependencies are ready. This is really important because you never want to slow down the delivery of experiment results based on just one experiment that might have slow dependencies. Key takeaways, so for scalability, try to dynamically pass and manage data dependencies, ensure independent experiment processing so that problematic experiments don't block the delivery of other experiments. Finally, putting it all together, I'd like to give you an abstract overview of our platform. The lifecycle of an experiment starts with the user configuring their experiments. In the configuration UI, I shortly touched on this step, how it can be improved through presets. The configs are then stored in our central database and consumed by our backend, which I haven't touched on in this presentation. But the backend basically consists of a experimentation service, mostly responsible for the randomization and for sending impression events. And the backend also contains SDKs for developers so that they can easily integrate experiments into their code bases. The experiment configuration, the impressions, and the metric data then get consumed by the data processor. It is responsible to run all the pre-aggregations on the discussed unit and variation level. And then these pre-aggregations are consumed by the analyzer that runs through all the statistical calculations. The data processor and the analyzer are scheduled via Airflow every day. And then the final step is that we are exposing all the experiment data in Looker, which is then ready to be consumed by the user. To close my presentation, I want to discuss future plans that we have. So as you can see, as you saw on the previous slide, you can see that we have a separate UI for configuring experiments and for analyzing experiments. Now in the future, we want to combine the two to create a one-stop shop for experimentation for all the users. Also, we already provide an API for ad-hoc calculations, but it's not very accessible for non-technical users. So we want to integrate this functionality into our UI. And we want to furthermore also support more experiment types using, for example, stratified sampling and bandits. And finally, when we have done this, we want to invest more time into non-technical pillars, like, for example, education and culture, so that we can push the independent usage of experimentation. And with that, I want to close my presentation and open the floor for questions.
Thanks a lot for the talk. We have lots of questions. So I'll start with the one with the most votes, is why not use an already existing service? That means software as a service. What is your current perspective on buying versus building?
Yeah, it's a topic that we are continuously discussing. Yeah, we are continuously evaluating it. The thing is, we already have a platform that works really well, and if we want to scale our experimentation even further, then the question is what brings the best ROI. But yeah, it's something that we constantly have in the back of our mind and constantly evaluating.
Thanks. Second question. Can you give an example for experiment? Is that mainly the usage of the website, like web analytics, or do you include more or different data sources?
Yeah, okay. Yeah, so this presentation was mostly about A/B testing in like internet companies, right? So famous example is changing, for example, the button color of a checkout button. So yes, we are always testing the user experience, one variation against the other.
Next one. How many experiments are you running? How many metrics are you defining for every experiment? Do you have some order of magnitude of the amount of the data you need to process every hour or day?
I can't talk about how many experiments we are running. Yeah, sorry, I can't disclose this information.
No problem. Next one. How did you do your experimental design? Did you use casual graphs, a DAG, with across a fundamental team to democratize casual inference and research design?
So in our experimentation team, we basically have two work streams. One is what we call product experimentation, where we run like traditional A/B tests like just described. And then we have another work stream with, which we call or refer to as marketing experimentation. And there we are more investing into causal inference, quasi-experimentation methods, and so on. But that's not something which is related to the presented platform.
Next one. have you experienced bottlenecks in running query-intensive experiments on some databases? How did you combat this?
Yes, so we are using Databricks, and behind we are using AWS, and because we have a daily batch process, it's not so big of a problem. However, for all those ad-hoc use cases, as I showed, when the analyst wants to recalculate experiment results, yes, then it's a bit annoying, but it might take 1 hour, for example, to get the results. We are trying to optimize this continuously, but with a significant amount of data, it's difficult. Either you are putting more money onto the problem and then you are running faster, or you are just accepting the runtime. So yeah, it's always a trade-off, basically.
Okay. Next question from Katarina. What is the update frequency of experiment data?
It's daily. So we are also investigating real-time data to really catch experiments that are significantly hurting the user journey, or for example, increases latency. We have monitoring on all this, but not necessarily split by experiments. But yeah, definitely something that we want to explore in the future.
Thank you. So we have a question from the audience. We need to speak on the microphone because of the remote attendees.
Thanks a lot for the presentation, really cool. You mentioned the specific feature that you built into your platform of reusing experiment configurations. Mm-hmm. So I suppose that you rerun a similar experiment at different points in time. And when doing that, did you also look into somehow reusing the learned information, for instance, via priors in like a Bayesian setup, and then maybe looking into credible intervals instead of confidence intervals? Is that something that was relevant to you, you looked into?
Yeah, so first of all, for the presets, so in those presets you can define as much information as you want. So if you are defining fewer information, then it's a more generic preset, right, that you can probably utilize for many different experiments, or you define many different input parameters, then it's very specified for a particular use case. So the user is free to choose how specific they want to create this preset. For the different intervals, so you asked about confidence intervals versus, what was it, Bayesian intervals, or? So we looked into this, but we didn't see so much value going into the Bayesian direction, just because it's not so easy, or we didn't find it really easy to specify relevant priors. And in the end, we didn't get very different results from just a frequentist approach versus a Bayesian approach. So that's not something that we have looked into anymore.
Thank you. I saw that we do have more questions from the audience. However, we need to finish already. So if you can, please contact him directly or ask the questions in the website and we forward to the speaker. Thank you a lot.